Also known as four-cycle, an internal combustion in which the piston completes four separate strokes which comprise a single thermodynamic cycle. A stroke refers to the full travel of the piston along the cylinder, in either direction. The four separate strokes are termed intake. This stroke of the piston begins at top dead center. The piston descends from the top of the cylinder to the bottom of the cylinder, increasing the volume of the cylinder. A mixture of fuel and air is forced by atmospheric or greater pressure into the cylinder through the intake port. Compression. With both intake and exhaust valves closed, the piston returns to the top of the cylinder, compressing the air-fuel-air mixture into the cylinder head. Power. This is the start of the second revolution of the cycle. While the piston is closed to top dead center, TDC, the compressed air-fuel mixture in a gasoline engine is ignited by a spark plug in gasoline engines, or which ignites due to the heat generated by compression in a diesel engine. The resulting pressure from the combustion of the compressed fuel-air mixture forces the piston back down toward bottom dead center, BDC. Exhaust. During the exhaust stroke, the piston once again returns to top dead center while the exhaust valve is open. This action exports the spent fuel-air mixture through the exhaust valves. Power output limitations. The four-stroke cycle A, intake B, compression C, power D, exhaust. Maximum amount of power generated by an engine is determined by the maximum amount of air ingested. The amount of power generated by a piston engine is related to its size, cylinder volume, whether it is a two-stroke or four-stroke designs, volumetric efficiency losses, air-to-fuel ratio, the calorific value of the fuel, oxygen content of the air and speed RPM. The speeds is ultimately limited by material strength and lubrication. Valves, pistons and connecting rod suffer severe acceleration forces. At high engine speed, physical breakage and piston ring flutter can occur, resulting in power loss, even engine destruction. Piston ring flutter occurs when rings oscillate vertically within the piston grooves they reside in. Ring flutter compromises the seal between the ring and the cylinder wall, which causes a loss of cylinder pressure and power if an engine spins too quickly. Valve springs cannot act quickly enough to close the valves. This commonly referred to as valve float, and it can resulting in piston-to-valve contract, severely damaging the engine. At high speeds, the lubrication of piston-cylinder wall interface tends to break down. This limits the piston speed for industrial engines to about 10 meters per second. Intake/exhaust port flow. The output power of an engine is dependent on the ability of intake air-fuel mixture and exhaust matter to move quickly through valve port, typically located in the cylinder head. To increase an engine's output power, irregularities in the intake and exhaust paths such as casting flaws, can be removed, and, with the aid of an airflow BWNCH, the Radia valve port turns and valve seat configuration can be modified to reduce resistance. This process is called porting, and it can be done by hand or with a CNC machine. Supercharging. One way to increase engine power is to force more air into the cylinder so that more power can be produced from each power stroke. This can be done using some type of air compression device known as supercharging, which can be powered by the engine crankshaft. Supercharging increases at the power output limits of an internal combustion engine relative to its displacement. Most commonly, the supercharger is always running, but there have been designs that allow it be cut out or run at varying speeds relative to engine speed. Mechanically driven supercharging has the disadvantage that some of the output power is used to drive the supercharger, while power is wasted in the high-pressure exhaust as the air has been compressed twice and then gains more potency of volume in the combustion, but it is only expanded in one stage. Turbocharging. A turbocharger is a supercharger that is driven by the engine's exhaust gases, by means of a turbine. It consists of the two-piece, high-speed turbine assembly with one side that compresses the intake air, and the other side that is powered by the exhaust gas outflow. When idling, and at low to moderate speeds, the turbine produces little power from the small exhaust volume. The turbocharger has little effect and the engine operates nearly in a naturally aspirated manner. When much more power output is required, the engine speed and throttle opening are increased until the exhaust gases are sufficient to spin up the turbocharger's turbine to start compressing much more air than normal into the intake manifold. Turbocharging allows for more efficient engine operation because it is driven by exhaust pressure that would otherwise be mostly wasted. But there is a design limitation known as turbo lag. The increased engine power is not immediately available due to the need sharply increase engine RPM, to build up pressure and to spin up the turbo, before the turbo starts to do any useful air. Increased exhaust and spins the turbo faster, and so forth until steady high power operation is reached. Another difficulty is the higher exhaust pressure causes the exhaust gas to transfer more of its heat to the mechanical parts of the engine. Rod and piston to stroke ratio. The rod to stroke is the ration of the connecting rod to the length of the piston stroke. A longer rod reduces sidewise pressure of the piston on the cylinder wall and the stress forces, increasing engine life. It also increases the cost and the engine height and weight. Diameter equal to its stroke length. An engine where the bore diameter is larger than its stroke length is an over-square engine. Conversely, an engine with a bore diameter that is smaller than its stroke length is an under-square engine. Valve train. The valve train are typically operated by a camshaft rotating at half the speed of the crankshaft. It has a series of cams along its length, each designed to open a valve during the appropriate part of an intake or exhaust stroke. A tappet between valve and cam is a contact surface on which the cam slides to open the valve. Many engines use one or more camshafts above a row or each row of cylinders, as in the illustration, in which each cam directly actuates a valve through a flat tappet. In other engine designs, a camshaft in the crankcase, in which case each cam contacts a push rod, which contacts a rocker arm that open a valve. The overhead cam design typically allows higher engine speeds because it provides the most direct path between cam and valve. Valve clearance. Valve clearance refers to the small gap between a valve lifter and a valve stem that ensures that the valve completely closes. On engines with mechanical valve adjustment, excessive clearance causes noise from the valves not closing properly. This results in a loss of performance and possibly overheating of exhaust valves. Typically, the clearance must be readjusted each 20,000 miles, 32,000 kilometers, with a feeler gauge. Most modern production engines use hydraulic lifters to automatic energy balance. Auto engines are about 30% efficient, in other words 30% of the energy generated by combustion is converted into useful rotational energy at the output shaft of the engine, while the remainder being losses due to waste heat, friction and engine access source. There are a number of ways to recover some of the energy lost to waste heat. Use of a turbocharger as diesel engines is very effective by boosting incoming air pressure and in effect provides the same increase in performance as having more displacement. The Mack Truck Company, decades ago, developed a turbine system that converted waste heat into kinetic energy that it fed back into the engine's transmission. In 2005, BMW announced the development of the Turbo Steamer, a two-stage heat recovery system similar to the exhaust gas that recovered 80% of the energy in the exhaust gas and raises the efficiency of an auto engine by 15%. By contrast, a systolic engine may reduce fuel consumption by as much as 40%. Modern engines are often intentionally built to be slightly less efficient than they could otherwise be. This is necessary for emission control such as exhaust gas recirculation and catalytic converters that reduce smog and other atmospheric pollutants. Reductions in efficiency may be counteracted with an engine control unit using lean burn techniques. In the United States, the corporate average fuel economy mandates that vehicles must achieve an average of 35.5 miles per gallon, (mpg), compared to the current standards of 25 miles per gallon. As automakers look to meet these standards by 2016, new ways of engineering the traditional internal combustion engine, ICE, could have to be considered.